So higher order differential equations. So we had just a quick review. So linear differential equations of second and higher order. What we had discussed is uh, the differential equation in which the dependent variable and its derivatives occur only in degree 1 and are never multiplied together. That is called as a linear differential equation. Now the general form of the linear differential equation is this. Nth derivative of y plus p1 times n minus first derivative of y plus p2 times n minus second derivative of y plus pn times x, y is equal to x. This p1, p2, pn are all functions of x alone, including this capital X. So then this is called as a linear differential equation of higher order, of the nth order. Now, but if the linear differential equation, we replace those p1, p2, p3, so on by constants. They are not functions of x, but they are replaced by k1, k2 up to kn. The right hand side can be a function of x, but all the coefficients are constants. Then we say that it is linear differential equation with constant coefficients. And x is a function of capital X is a function of small x. Now, when capital X is equal to 0, then we call the equation as homogeneous, because y and its derivative, every term has degree 1. Here, the right hand side term has degree 0 for y. But anyway, because if this term does not exist, it means that all the terms are of degree 1. In terms of degree, we are looking for y and the derivatives of y only. So when x equal to 0, it is called a homogeneous equation. When x is not equal to 0, it is called as the non-homogeneous equation. So for homogeneous equation, the solution is like this. If C1, if y1 and y2 are two solutions and C1 and C2 are arbitrary constants, then C1y1 plus C2y2 will also be a solution of the differential equation, because of the addition principle of derivatives. So because of the sum rule of derivatives, this thing holds. So a complete solution of the nth order homogeneous differential equation will have n functions, y1, y2, yn, and it will be a linear combination of these functions, c1, y1 plus c2, y2, so on up to cn, yn. So where c1, c2, c3, and cn are arbitrary constants. So now this is the complete solution or the general solution of a homogeneous differential equation. So C1, C2, Cn are arbitrary constants, and y1, y2 up to yn are linearly independent functions. They are linearly independent functions. They're not dependent. One cannot be written in terms of multiple of other, or a combination. One cannot be written in terms of linear combination of the others. They're all independent functions. Then basis, the linearly independent functions, this is called as the basis of the the system of differential equation. And particular solution is obtained by giving specific values to the arbitrary constants in the general solution. So these are definitions. And then for non-homogeneous equation, you get x on the right hand side. So when we get x on the right hand side, now if U is the complete solution of homogeneous equation and V be the particular solution of the uh, non-homogeneous linear differential equation, then we can write this equation A and B. Equation A is the homogeneous component because U is a solution of the homogeneous equation. So U satisfies this equation. So we can write this. And V is a particular integral or a particular solution for the non-homogeneous differential equation. So V will satisfy the original given equation. Now we can add these two. When we add by sum of derivatives rule, the sum rule, this gets added. So what we can see is that y is equal to u plus v is the solution to the given non-homogeneous linear differential equation. So for a non-homogeneous equation, the solution will include the solution of the homogeneous part plus the particular integral. So u is called as the complementary function and v is called as the particular integral. And then we had discussed about the operator d. The operator d by dx is d square by dx square is capital D square, d cube by dx cube is capital D cube, so on. So the given differential equation can be written like this. Nth derivative of y can be written as d power ny. This is for ease of writing. Instead of each time writing d by d power n by d x power n, we can use this operator that makes things easier. So d power n y plus k1 d power n minus 1 y plus k2 d power n minus 2 y plus k and y is equal to x. So if we take y common, we get a polynomial in d. So, and this can be factorized. So up to here, we discussed this. So now let us go further. So now let us actually discuss this part. Solution to linear differential equation with constant coefficients. Both, this is a non-homogeneous equation. So homogeneous part and the non-homogeneous part, both will be there. So methods to find complementary function. So consider this equation now. So consider the homogeneous part of the differential equation. So it is d power n plus k1 d power n minus 1 plus k2 d power n minus 2 plus kn times y is equal to 0. So we have written the homogeneous part of the differential equation like this. Okay. Now y equal to 0 is one trivial solution, meaning but we don't want that kind of a solution. Y equal to 0 is a solution that is by default. So this function itself doesn't exist. That means, so y equal to 0. So we have to find, other than, we are looking for solutions other than y equal to 0. Therefore, we need to solve the polynomial in D. We need to solve the polynomial in D. What is this? D power n plus k1 d power n minus 1 plus k2 d power n minus 2, so on, plus kn should be equal to 0. This cannot be 0, so this has to be 0. Now, this equation is called as the auxiliary equation. This equation is called as the auxiliary equation. It is the polynomial equation containing the differential operator D. Okay. Now let M1, M2 up to Mn be the roots of the auxiliary equation. Because a polynomial of degree n will have n roots. Okay, this is the fundamental theorem of algebra. Polynomial of degree n will have n roots, either real or complex. So now let us consider cases. If all the roots of the auxiliary equation are real and different. This is the first case. Okay. In this case, we can write the homogeneous linear differential equation as D minus M1, because the roots of the polynomial, right? So the polynomial we can write like this: D minus M2, D minus Mn times y equal to 0. There's a polynomial if it has n roots and all are real and different, then by factors theorem, D minus the root will be a factor. So you will have n factors multiplied by y. This equation here becomes this. So now let us take any one of them. Let us consider the ith root, mi. So when y gets multiplied by any of these factors, it may give 0. This minus any of the factors will give 0. So then So d minus mi times y is equal to 0. So now this is a solution. We get now dy minus miy is equal to 0. So this is dy by dx is equal to mi by y. So this is variable separable form. This is a linear differential, so this is a differential equation of first order, first degree. So the solution, okay, solving the differential equation, we get this. We get log y, sorry, this is dx. We get mix plus, let us say, log ci. So this implies y is equal to ci e power mix. Removing the log, we get this. Therefore, this is the solution. Okay. Now, for I equal to 1 to n, if we vary, we get all the, for each factor, we'll get a solution. So thus, the complementary function or the general solution for homogeneous linear differential equation is y is equal to c1 e power m1x plus c2 e power m2x plus so on ci e power mix cn e power mnx. This is the complementary function. Complementary functions looks like this. It is very simple. C e power m1x plus okay, or you can simply write this as summation of I equal to 1 to n ci e power mix. This is when the roots are real and different. So this is the complementary function. Very important result. Next, case 2. If 2 or more roots are equal, okay, this is case 2. So let us take a sub case in this. If 2 roots are equal, say m1 is equal to m2, but all others are different, let us say, then what we get is this. Then the solution, so m1 m2 solution of m1 and again m2, which is m1, times y equal to 0, will satisfy the differential equation. See, understand our philosophy, how we are finding the solution. Each factor multiplied by y. Now the factors were different. Now the factors are identical. So how do we do it? So, okay. So here we will assume this as z. So let d minus m1 times y be equal to z. Then d minus m1 times d minus m1 times y equal to 0 will imply d minus m1 times z equal to 0. Now solution for this implies z is equal to, say, c1 e power m1x, the solution. How did we get this? Because from the previous case, when d minus mi times y equal to 0, the solution for this is y equal to c1 e power mi times x. So c1 e power m1 times x will be this z. Now this z you replace. So now so this is this. Okay. Now substituting. Now what is z? Now since d minus m1 times y is equal to z, we have dy by dx minus m1y is equal to c1 e power m1x. This is a linear differential equation. This is a first order linear differential equation. Its solution is you have to find the integrating factor. Integrating factor is e power integral p dx, that is e power minus m1x. So solution to the above linear differential equation is first order y times integrating factor is equal to integral of q times integrating factor dx plus c. All right, plus whatever the constant is. I'll put as k, then we will change this. So I will write this as y times e power minus m1x is equal to integral q now is this c1 e power m1x times the integrating factor plus okay, whatever we can write. I'm writing k at the end, we'll change it to c1 or c2, whatever. Okay, now this becomes y equal to e power minus mx. This becomes c1x plus k. I will choose to write c2 here. Okay. So therefore we get y as c1x plus c2 times e power m1x. Very, very useful. Okay. Now, therefore, the complementary function or the general solution of the given nth order homogeneous linear differential equation will be y is equal to, because m1 and m2 are equal, so y for m1 and m2 together we get c1x plus c2 times e power m1x plus c3 e power m3x. All others are different. This will be the complementary function. All right. Now, case B, if there are three equal roots, and again, same fashion we can solve. Let's say m1 equal to m2 equal to m3. Okay. Then the complementary function, we will not go through the whole thing again, but I'll write directly complementary function of the homogeneous LDE will be y is equal to c1x square plus c2x plus c3 times e power m1x. Then we have m4 c4 e power m4x plus c5 e power m5x, so on. Okay. So now if say m1 equal to m2 is equal to say some k1, and m3 equal to m4 equal to m5 equal to k2, and rest of the roots are real and different, then the complementary function will be y, two are equal, right? So you get c1x plus c2 e power k1x, because m1 equal to m2, plus now three are equal, m3 m4 m5, so c3x square plus c4x plus c5 times e power k2x, because it will be of this form. If three roots are equal, it will be of this form. So it becomes a quadratic, and if four roots are equal, this will become a cubic. This just goes on. Now, plus rest are all different. C6 e power k6x and cn e power knx. So This is when roots are real and equal. Okay. Okay, so this is the form. This is easy, fairly standard to remember when roots are equal. Now, let us take the third case. If imaginary roots or complex roots always occur in conjugate pairs. So, if one pair of roots are complex or is complex, one pair is complex. So, then, let M1 be alpha 1, or we'll just write alpha plus I times beta, and M2 is alpha minus I times beta. Okay. Now, how do we find the complementary equation? So then the complementary function. Then the complementary function becomes C1 e power alpha plus I beta plus C2 e power alpha minus I beta plus C3 e power M3x. Oh, sorry, this should be multiplied with x plus C4 e power M4x. So we get like this. Now we will look into how to simplify this part. So now we shall simplify the first two terms. So we get C1 e power alpha plus I beta times x plus C2 e power alpha plus I alpha minus I beta times x will be equal to e power alpha x can come out, and we get C1 e power I beta x plus C2 e power minus I beta x. Now this becomes e power alpha x. Alpha is the root. Now this part will be, you see here, using the Euler's identity of complex number. E power I theta is cos theta plus I sin theta. Okay. So this becomes C1 times cos beta x plus I sin beta x plus C2 times cos beta x minus I sine beta x. Now we get e power alpha x times, take this C1 plus C2 cos beta x plus I times C1 minus C2 sine beta x. Okay. Now, what we can do is we can replace this with A and B. We can write e power alpha x times A cos beta x plus B sine beta x. This is a constant. It's a number. Complex, but it's a number. Right. So we can replace it with A and B. So now we understand that if the roots are imaginary, then the solution will be a sinusoidal waveform. Very, very important. Extremely important in any dynamic problems, be it mechanical vibrations, simple harmonic motion, or the mechanical vibration problems. This is the one. And even in alternating current circuits, LCR circuits, in the solutions, you get cos beta sine beta, because alternating current means you can model it as cos plus I sine. So it's a sinusoidal waveform. So in alternating current circuits also, we get this solution. So anything to either in electricity or magnetism or mechanics, this is the solution. It gives a vibrating waveform. Now depends on alpha, how the waveform looks like. We get this way. Now let us say, so now the complementary, therefore the complementary function can be written as y is equal to, the first one will be e power alpha x, the real part, times, this is a b. I will replace this a by C1, capital C1 cos beta. It is some constant, right? Don't take this as this C1. C2 sine beta x plus C3 e power m3x plus C4 e power m4x Cn e power mnx. This is the complementary function. Now, further case in this, if two pairs of complex roots are equal, that is a possibility. Let's say m1 equal to m2 is equal to alpha plus I beta, and m3 equal to m4 is equal to alpha minus I beta. Then the complementary function will be of this form. E power alpha x will be common. Then just like we did for the two equal roots in the case B, you get C1x plus C2 times cos beta x plus C3x plus C4 times sin beta x. Then remaining thing are as it is. C5 e power m5x, Cn e power mnx. So this is the complementary function, and suppose three pairs are equal, then you will get C1 x square plus C2x plus C3 times cos beta, and C4x plus C4x square plus C5x plus C6 sin beta, and so on. So this is the method to find the complementary functions. So these are, so let's take examples. All right, the first one, solve d square y by dx square plus dy by dx minus 2y equal to 0, given y of 0 equal to 4 and y dash 0 is equal to minus 5. Okay, so let us solve this. So the given equation is can be written as d square plus d minus 2 times y equal to 0, where d is dy dx. So this is the auxiliary equation. Solution to the auxiliary equation. All right, so we can factorize this. This is, we get d plus 2 into d minus 1 equal to 0. Therefore, the roots are minus 2 and 1. Okay, they are real and distinct. Therefore, the general solution or the complementary function is y equal to C1 times e power minus 2x plus C2 times e power x. So this is the solution. Now given y of 0 equal to 4, this implies 4 is equal to C1. You substitute 0, we get this. C1 plus C2 is equal to 4. We have to find C1 and C2. This is equation 1, solution, this is 2. Now y dash 0 is equal to minus 5. So first differentiate y dash, differentiate y. We get minus 2 C1 e power minus 2x plus C2 e power x. So y dash 0 equal to minus 5, which is minus 2 C1 plus C2. So solving 2 and 3. So you get C1 plus C2 equal to 4 minus 2C1 plus C2 is equal to minus 5. When we subtract, we get 3C1 plus 0C2 is equal to 9, which implies C1 is equal to 3. If C1 is equal to 3, C2 will be 4. Sorry, C2 will be 1. C1 is equal to C3, C2 will be 1. So therefore, the solution is y is equal to C1 is 3. This is the solution. C1 e power minus 2x, 3 e power minus 2x plus C2 is 1 e power x. So this is the solution. Okay. This is a particular solution because the boundary conditions are given or the end conditions are given. So we can find the arbitrary constants according to these conditions. So this was a simple question on real and unequal roots. Next, we'll solve other one. Solve d square y by dx square minus 4 dy by dx plus 4y equal to 0, where given is y of 0 is 3 and y dash 0 is 1. So solution, the linear differential equation can be written as d square minus 4d plus 4 times y equal to 0. Now solution to the auxiliary equation. This is a perfect square. So d is equal to 2, 2. So real and equal roots. Therefore, the general solution is y is equal to c1x plus c2 e power 2x. This is a solution, right? m1, m2 are equal to 2. Okay. Now, given this, this is the general solution. Now, it is said, it is given that y of 0 equal to 3 and y dash 0 equal to 1. Now, y of 0 equal to 3 gives us 3 equal to, this is 0, c2, okay, c1 times 0 plus c2 times e power 0 is 1. So we get c2 equal to 3. Next, y dash derivative is c1x plus c2 times 2 e power 2x. UV rule we have to apply. And then differentiate this one. Keeping this as it is, differentiate this one, we'll get c1 times e power 2x. So now y dash 0 equal to 1. Substitute. So we get C2, 2C2 into 1 plus C1 into 1. So C2 we already found as 3. So C1 is 1 minus 2 C2. So 1 minus 6, which is equal to minus 5. So C1 is minus 5, C2 is 3. So 3 minus 5x. Therefore, the particular solution is y is equal to 3 minus 5x times e power 2x. Got it? Hmm. Okay, let's do other problems. Third one, solve. D square minus 2d plus 4, the whole square times y equal to 0. Okay, it is just a general solution, not a particular solution. So we need to solve this. Okay. Look at the discriminant. Discriminant is b square, that is 4 minus 4ac. 4 times 4, 16. So discriminant is negative. So it is a complex roots. You get complex roots. D square minus 2d plus 4 equal to 0. This implies d is minus b plus or minus root of b square minus 4ac upon 2a. So we get 2. This is 12 minus 12. That is 4 into 3. So I into 2 root 3 by 2. So we get 1 plus or minus root 3i. This is d. Now, therefore, the solutions to d square minus 2d plus 4 whole square equal to 0 is, you get 2 equal roots because it is a square, perfect square. So let's say m1, m2 is 1 plus root 3i, and m3, m4 is equal to 1 minus root 3i. Okay, where mi are the roots of the auxiliary equation. So these are the roots. So therefore, the complementary solution or the general solution is y is equal to e power alpha x. So first e power alpha is 1. So e power x times. Then we have c1x plus c2 times cos beta x root 3x plus c3x plus c4, because the roots are repeating. That's why. Sine root 3x, sine beta x. This is the general solution. And of course, when you put conditions, we will need 4 conditions here to get C1, C2, C3, C4. If these 4 conditions are put, we will get 4 roots. Next, fourth one, solve. D cube, sorry, D square plus 1 whole cube times y equal to 0. Solution. D square plus 1 whole cube equal to 0 means the roots are I and minus I. These are under plus or minus under root of minus 1. So I and minus I. So you have I, minus I, minus I, minus I. 3. Okay. Therefore, this I, minus I, minus I, minus I. So therefore, the solution alpha is 0, alpha plus I beta. Alpha is 0, beta is 1 basically. Plus I beta, alpha minus I beta, right? So 1. So general solution y is e power 0 x, that is 1. Now 6 arbitrary constants you'll get. C1 x square plus C2 x plus C3 times cos beta x plus C4 x square plus C5x plus C6 sine x. So this e power x can be replaced by 1. So we get this as the solution. Okay. So I'll give you some problems for practice. You please solve them. Before the next class. Or you can take any textbook and attempt to solve. So this is the 5th question. Solve d cube plus d square plus 4d plus 4 times y equal to 0. D power 4 x upon dt power 4. So dependent variable is x, independent variable is t. So be careful what it is. So x will be in terms of t function. That is what we need. Then okay, you can attempt this. So next class we will do the particular integral. So today we did the complementary function, how to evaluate the complementary function. In the next class we will see how to solve the particular integral. Okay, we'll stop here now.